Good afternoon, everyone. Right now, I am prepared to present my presentation, which is prepared for the assignment to submit in the faculty induction program sponsored by Jajpur University. All faculty members of Jajpur University and FIP team are welcome in this presentation and in making this video with the FreeCam, which is a very good screencasting software. So I now start my presentation. Okay. So this is my presentation, PowerPoint presentation, and here okay. Welcome to the presentation on Hilbert Space in functional analysis. Myself, Dr. Vishnu Devnath, Assistant Professor, Department of Mathematics, Rajiv Gandhi University, Eternal. The main objective of this video content is to prepare a brief lecture on Hilbert spaces in functional analysis, which is a topic of PG courses, especially for MSc students. I hope this lecture or e-topic will be very helpful and useful to motivate the students of PG courses and research scholars also. As you know that Hilbert space is a crucial concept in functional analysis which plays a significant role in mathematics and physics and some other domains also. The completeness property of the space and inner product structure make it a powerful tool in various applications. The entire talk is divided into 7 sections. The first section is non-linear space, second one inner product space, then Hilbert space, and examples, some key features and characterizations, and finally applications, various fields. Non-linear space. Non-linear space. A non-linear space is a vector space X together with a function from the vector space X into the scalar field F, where this field may be the field of real number or complex number, and this function is said to be normal on X, and which satisfies these four properties. The first property is the non-negativity property, and the second one is nullity property. That is, norm of X is equal to 0 when only X is null. This is why this property is called nullity property. Then the homogeneity property, the triangle inequality property. Now, inner product space. An inner product space is a vector space X together with a function from the product space X cross X, Cartesian product of X twice, into the set of field F. It will be field. Here R will be F, where F may be the field of real number or field of complex numbers, such that it satisfies these 4 properties. The first property is non-negativity property, the second one complex conjugate property, third one linearity property on the first coordinate, the last property is the homogeneity property. Now Hilbert space. At the beginning of 20th century, the German mathematician David Hilbert first described the Hilbert space while working in the domain of integral equations and Fourier series. Hilbert space is defined by H here, and it is defined as a vector space on which an inner product is defined in such a way that the space is complete with respect to the norm induced by inner product. Now examples of Hilbert spaces. Every finite dimensional inner product space is Hilbert space. For example, the n-dimensional Euclidean space is a Hilbert space with respect to the inner product defined as the dot product. This one is the property of a dot product, or the definition of dot product here. So if we define the inner product in the Euclidean space as equal to the dot product, then this space becomes a Hilbert space. Similarly, the space of square summable sequences is also Hilbert space. The space of square-integrable functions is Hilbert space. The space of polynomial functions defined here, defined in this fashion, is a Hilbert space. So many more examples of Hilbert space we have. Here we shown only 4 examples. Now the completeness, which is the crucial property of Hilbert spaces. Before defining completeness, we first define Cauchy sequences. A sequence Xn in Hilbert space H is said to be Cauchy sequence if the norm between the difference of xm and xn tends to 0 as mn tends to infinity. Now completeness. A Hilbert space H is said to be complete if every Cauchy sequence converges to a limit point x, where x must lie in the Hilbert space H. Now key features of Hilbert space. Orthogonality. Two vectors x and y of Hilbert space are said to be orthogonal if the inner product is 0. Orthogonal complement. The set of all vectors of the Hilbert space H which are orthogonal to the subspace M is called the orthogonal complement of M. Then orthonormal basis. A basis composed of orthogonal unit vectors. Orthogonal unit vector, that is, if the norm or length of each vector in the basis set is unity. Now characterizations of Hilbert spaces. It's a very important theorem. Every Hilbert space is a Banach space, but the converse need not be true in general. But the converse will be true if the parallelogram law holds in Banach spaces. Now another important theorem is projection theorem. If M is a closed subspace of a Hilbert space H, then H is the direct sum of M and orthogonal complement of M. Applications. Hilbert spaces has wider of applications in quantum mechanics, statistical mechanics, quantum field theory, signal processing, cryptography, and many more domains. Thank you everyone. This was my presentation. I completed it in 12 slides. Now, no problem.